Let's look at acid-catalyzed hydrolysis of a nitrile. Remember that hydrolysis is adding water. If other reactions dehydrate or condense, hydrolysis will be adding water back in somewhere, somehow. So as we look at a nitrile, we can see that, let's compare. These are different derivatives of acids. So here's a carboxylic acid. This is an amide. And a nitrile is a derivative of those. It has 3 bonds to nitrogen, which is more electronegative than carbon. The acid and the amide also have 3 bonds to something more electronegative than carbon. So they're all carbons with the same oxidation state. So we can go between them without doing oxidation or reduction. So first step of hydrolysis of an acid will be that the nitrogen will pick up an acid. The nitrogen of the nitrile will pick up an acid. We're in the presence of water. Water is also here. And then water being present can now attack that protonated nitrile and shift electrons over to the nitrogen. Then in the next step, you can see water is added. We have a protonated water sitting on there. And so water itself can come along, take away that extra proton, and shift the electrons back to the oxygen. Now we've got our oxygen present, and what we can do is see how there's a resonance pair here. So I can move electrons around between these, and if I shift electrons down from this oxygen, that will push them onto the nitrogen, and so that's what you see here. So I'll just add in those electrons. I can shift this out here and over onto the nitrogen then, and we'll get our double bond and the electron pair on the nitrogen. So then water present will take away the extra proton here and shift the electrons onto the oxygen itself. So there's our amide. Okay, and in this process we started with H3O plus and we ended with H3O plus. But let's continue because there's more. That's just the amide. So on the second page we can go from an amide to an acid. So basically, I'm not even going to stop in my reaction mixture. I can just keep going. That oxygen can pick up the proton from that H3O plus that's still present. We'll have a protonated oxygen then. And water can attack that carbonyl just like it did before, shifting electrons up to the oxygen. We get 2 lone pairs now on it. And I seem to have 2 oxygens on that carbon and a nitrogen. I think you can now see where we're headed. So the water will take away the extra proton, shifting the electrons to the oxygen. And that gets us right down here. So now I have 3 bonds to something. You can see the oxygen, 2 bonds to oxygen, and a bond to nitrogen. So I continue to have 3 bonds to something more electronegative. I'm just shifting electrons around. So what I'll do now is use this electron pair to take the proton from, pick up an acid proton. And if you just put H plus, that would be okay. Water is going to come in here in a moment. So now I have a protonated nitrogen, and I'm going to bring electrons down from the oxygen. And that will release this as a neutral leaving group. There's our ammonia with its lone pair, and we have a protonated oxygen. So last step, this ammonia is pretty basic. So it will take that proton, shifting the electrons to the oxygen, and we'll end up with our carboxylic acid plus NH4 plus. So that is how we can go from a nitrile all the way to an acid. And note that these are equilibrium steps, which means I can start at an acid and go back to a nitrile if I remove water. I have another reagent that will make this easier though because it is dehydrating.